So I did get one email this morning asking for help with questions 6 and 7 on the lab assignment that you're going to do this week in lab, and they get submitted next week. So questions 6 and 7 focus on determining the number of different stereo and conformational isomers you can have with. For number 6, it's dimethyl cyclopentane, and then for number 7, it's methyl cyclohexanol. So when you look at dimethyl cyclopentane, basically you can put these CH3 groups in two places. Now, obviously, hopefully you can see this. There's one, when you put it really doesn't matter like where you put the first one. It's the second one that sort of matters. So really we only, in terms of unique positions, we have 3 possibilities as to where we can stick the second methyl group. Now, first possibility is at the first carbon. This will give us the 1,1 dimethyl. And just to reassure you, for the Chem 1 students, Orgo 1 students, you're not going to have to name these compounds yet. That's what we're going to get to next. Second option is 1,2 dimethyl. And the third option is 1,3 dimethyl. Now, within each of these, we have to determine if there is a possibility for a chiral center. So for this one, it's not possible. So this is the only possible way we can combine these two. Like, there's no stereoisomers associated with this. Now, with this, there are 2 ways we can do it. And unfortunately, I left my modeling kit in the lab. So basically, we have what's called the cis. So if we were to take that, if you were to build your 5-member ring and press it down flat, we would have a scenario where they're both on top of the ring. And then we have a possibility where they're both, well, they're opposite sides of the ring. So we have cis and trans. Now, because we have 2 stereo centers, that gives us the possibility of up to 4 possible stereoisomers. Now, the next thing you need to ask yourself is, do I see a mirror plane? So with the cis one, we do see a mirror plane. And because we see a mirror plane with these 2 chiral centers, this ends up being a meso or meso. It's basically not a chiral molecule. It's meso. So there's only one possibility. Here we have, with the trans, there's no mirror plane. So we have both options. We have this, then we have the one where we have the enantiomer. And we're going to do the same type of analysis for the 1,3 dimethyls, that we look at both the cis where they're on the same side, the trans where they're on opposites, see if we see a mirror plane. And then if we do see a mirror plane, we know that we don't have it in enantiomers. We're swapping the wedges and the dashes. So how about the second problem, which is the methyl cyclohexanol? Well, it's a similar approach, but that hexanol there is going to create problems in the sense that you're not going to get any meso complexes. So with cyclohexanol, we have 6 carbons, and we've got a methyl, and we've got an OH. Now, first position doesn't really matter, so I'm just going to stick the OH group on. And we have 4 unique positions. One where they're both bound to the same carbon. We have the 1,2, 1,3, and the 1,4. Now, we're going to do a similar thing like we did before. So for the first one, this isn't chiral because we have the ring on both sides. So the first one, there's only one combination. For the second one, we need to consider both the cis and the trans, and we need to see, so if they're both wedge or if they're one wedge and one dash, and we need to see if we see a mirror plane. Now, because of this OH group, we break up the symmetry, so the spoiler alert here is there are no mirror planes. So since you have 2 chiral centers, there are 4 combinations that you can draw of this. And the same will be true for the rest of these. Because there are 2 chiral centers, we can draw 4 different stereoisomers. And then from there, you need to draw the Fisher projections just so you can kind of get a feel for how to draw the Fisher projections. But this is how you approach 6 and 7. For what basically what it's doing is giving you 2 functional groups to stick on the rings. You can stick them. There's only a handful of unique ways to draw them. Take the individual drawings, the relative configurations, which are shown here without the wedges and dashes. See if it generates a stereocenter. If it does, see if you get a meso complex by looking for a mirror plane. If it's not meso, then you've got, based on the number of chiral centers, to the impossibilities of stereoisomers. So that's question 6 and question 6 and question 7 on the lab work that's being done this week. And just a reminder, you have until your lab period next week to finish those. You are free to ask me any questions about them. This is not a test. This is to make sure that you're understanding the material, because when we start moving into characterization, it's going to kind of be assumed that you can read these kind of diagrams, that you understand how many hydrogens are there, and you understand how they're all connected to each other. And you're going to know what chiral centers are, because you have to know that for polarimetry. So again, I'm less concerned about you being able to do this all on your own, more concerned about you understanding it. So if you have questions, feel free to ask them during the live streams, as well as also during the labs this week. So any questions for people watching, any questions from people who are watching? I only see one person. So got a question, can we do number 11 in the homework on Connect? So let me log into Connect. Right, so let me share the desktop with you so you can see what's on my end. Now, again, the homework tends to draw from polls, so if you're not seeing your exact question, that's fine. This is more kind of just the spirit of what the homework is asking for. So what it's asking you to do is relate these compounds on whether or not they're the identical molecule, whether they're a resonance structure, whether they're an isomer, or whether they're neither. So let me draw these up on the board really quick, and we'll talk about how you get to the various answers. All right, bring it back to my screen. So our starting compound right here is this alkene ketone complex. So this is what we're going to compare the other ones to. Now, first thing I'm going to ask you is, well, it asks you how are they related. So let's look at resonance structures first. So a resonance structure meets the criteria that we haven't moved any atoms around. So atoms still contain this, are still bonded to the same things. What we have changed is where double bonds are and where lone pairs are. So again, we shouldn't see any atoms moving. If we just looked at the atoms themselves, it would be in the same place. We're questioning whether or not we converted a lone pair to a double bond or a triple bond, or whether we converted a bond to a lone pair. So if we compare the first one, this isn't the case. We've moved atoms around. So this carbon contained one hydrogen. Now this one contains two, so these are not resonance. Here we've definitely changed the structure. Here it's still the same number of atoms. So we still have one oxygen, one hydrogen, one hydrogen, one hydrogen here, one hydrogen here. What we've done is, in this case, is that we've moved the double bond over. So basically we've taken this electron, moved these electrons over to form a double bond, and we've kicked the electrons up here. Now, you're also going to kind of pick up on resonance when you start seeing charges too. So if you start seeing charges, that's usually an indication that you've got some type of resonance structure, because we are moving electrons around, which can generate formal charges. So this is definitely a resonance structure. In terms of this one, actually if we just look at it, it's a mirror image. So if we took the mirror image of this, we'd get this. This isn't chirality, so we're not seeing any stereocenters here. So that would definitely make this identical. And in terms of resonance, this is definitely not a resonance structure because we've changed the number of bonds in it. So we haven't moved electrons around like we have here. So the next option it gives you is, are they isomers? So isomers meet the criteria that they're the same chemical formula, it's just that there's differences in how the atoms are bonded to each other. Now within isomers, we definitely have subclasses. So stereoisomers are ones where all the atoms are connected to the same thing, but spatially there's different arrangements. Conformational isomers have everything's connected the same, just spatially they're different because of rotations around single bonds. Constitutional isomers are ones where things are actually bonded differently. So when they say isomers, they're really kind of saying like any possibility where we see differences in bonding. So here, this would be an isomer. Because it has the same chemical formula, we just have the double bond in a different place. So we've also got hydrogens in different places. There's two hydrogens here, whereas there's only one hydrogen here. So this would be a constitutional isomer. This atom, let's see, we've got the same number of carbons. I'm going to gander the same number of hydrogens. I'm sorry, I'm going to cheat really quick and look at the key. Yep. So if we write out the chemical formula for this one, and this one, we're going to get the same chemical formula. So this also makes this one an isomer. Now our last one down here, we actually have two additional hydrogens in the formula that aren't here. So it's definitely not an isomer, it's definitely not a resonance structure, it's definitely not identical, so it ends up being our last option, which is neither. This compound and this compound are not the same thing. So that's how you approach that type of problem. Again, with resonance, resonance is a little bit trickier one to pick up, but resonance you're going to see lone pairs being converted to bonds and bonds being converted to lone pairs, and you will probably, with most resonance structures, start seeing changes in formal charges as well. For isomers, it's the same chemical formula. There are different types of isomers, but definitely if they have the same chemical formula, they are isomers of one another. And identical, like typically with identical molecules, I mean, you're typically just going to see like a rotation or a flip. Now, the tricky thing with identical is stereoisomers. Stereoisomers, particularly if it's a chiral molecule, the mirror image is not the same thing. So they are isomers, but they are stereoisomers. So you just need to make sure like you haven't changed, you don't see any stereocenters in here that would change that. So hopefully that answered your question. Any other questions out there? question got asked on number 12. It says C10H14 is wrong and why. So let's see if it's actually going to bother to let me see it this time. So question 12. The general molecular formula for alkanes is C4H2N plus 2. What is the general molecular formula for cycloalkanes? So it's not looking for numbers, it's looking for a formula. So where it gave you CnHn plus 2, you need to have a kin formula, so something with CnH as a function of N. Also, C10H14 wouldn't be a cycloalkane anyway. So for an alkane itself, that CnH2n plus 2, if you had C10, it would be H24. And then it's a different formula for the cycloalkanes. Honestly, I might pull these questions. These look like these were actually meant to be for the alkane chapter. Which leads me to believe that this problem was actually not what it showed me when I looked at it. Yeah, let me update the homework after this live stream. Yeah, I'll probably get rid of questions 12, 13, and 14. My guess is when I saw the question, it asked just a general concept about alkanes, not something that specific. Because 15 and 16 are definitely focusing on isomers, which I want you to know. Actually, it would be CnH2n without the 2's. So when you form that carbon-carbon bond, so we can start with something as simple as propane. So this has C3H8. When we form the loop, it's C3,222H6. So whereas this follows H2n plus 2, this follows CnH2n. But I'm going to get rid of questions 12, 13, and 14. My guess is that when I saw the preview to the problem, it didn't look like that. That's more of a test 2 material. But everything that follows it is definitely following isomers, which is what I want you to understand how isomers work. Again, Camille, I wouldn't worry about it. I'm going to eliminate those three problems. The intent was to get you to deal with isomers, but not to not it. The point of those questions was to get you to look at isomers and understanding how isomers are related. But it looks like that question is actually more just asking what's the general form of alkanes, which we'll cover on the next test. So I would not worry about questions 12, 13, and 14. I'm going to pull them off. That's 4101, 4102, 4136. Yeah, I just saw a version of the question where it asked about isomers, so that's why I put that makes sense and why I added that question when I first saw it. Good to know. So Camille, you should no longer be seeing that question on your homework. So when we talk about chirality in organic 1, we're going to focus specifically on carbon being chiral. Now, other elements like nitrogen and oxygen in principle can form chiral complexes, but with those, the chirality is associated with the lone pair, and there's free rotation of the lone pair. So they are chiral, but they're like that chirality interconverts a lot. So for the case of organic 1 and 2, we're going to say that chirality only applies to carbon. If you go on to take inorganic chemistry, you're going to learn that the definition of chirality in organic chemistry is actually a very specific subset. There are better definitions. You can have transition metals that are chiral. You can have lots of complexes that are chiral. So we define a chiral. When we talk about chirality, we actually have two types of chirality we have to discuss. Specifically, we have whether or not an atom is chiral, or if a molecule is chiral. So atoms can be chiral, but the molecules they're in may not necessarily be a chiral molecule. So we can talk about atomic chirality or molecule chirality. When we're talking about atom chirality, we're going to stick to carbon. And again, this is just for simplicity. Higher level courses will teach you how to spot chirality in other situations. Now, for a carbon atom to be chiral, it has to have 4 groups attached to it. So if we have something like an alkene, the carbons in the alkene are not, so if we have carbon with a double bond or triple bond, it's inherently prohibited from being chiral. If we have carbon double bound to an oxygen, because it's only going to have 3 things bound to it, it's inherently not chiral. So it has to be a carbon with 4 bonds coming off of it, and the 4 groups have to be different. And we'll talk about this in lab tomorrow. We'll actually go through how to demonstrate chirality using a Fisher projection, which makes it a lot easier. But if a carbon atom contains 4 groups bound to it and all 4 groups are different, the atom itself is chiral. We call it a chiral center. Any carbon that doesn't meet those conditions is considered an achiral carbon. Now, for a molecule to be chiral, it must contain at least 1 chiral center. And it can't contain a mirror plane. So if it meets both these conditions, the molecule itself is considered chiral. If it doesn't meet both conditions, it will either be considered achiral or meso. So if it doesn't contain the chiral centers, that makes it pretty easy. It's just an achiral molecule. If it contains chiral centers, but it contains a mirror plane, so an example of this would be cis 1,2-dimethyl cyclopentane. There's a mirror plane running through this molecule, so it looks like we reflected this half of the molecule into this half. In this case, this would be considered a meso or meso complex. So what happens in this case is that even though both these carbons are chiral, their chirality ends up canceling it out. When we start talking about polarimetry, we'll start talking about optical rotation. Physically, what's happening is that if you really work it out, these basically have opposite chiralities. One's S, one is R, one is S. And because these carbons look exactly the same, one carbon will bend the light one way, and the other carbon will bend it back the other way to the exact same degree. So it ends up not having optical activity. Now, in terms of symmetry, what ends up happening is that these two are mirror images of each other, so because they're mirrors, they cancel each other out. But again, you need to take like an inorganic chemistry course where they start talking more about why these mirror planes create this effect. But for now, I hate to qualify that for you, but it does need to be this size. For now, we're going to focus only on carbon being chiral. Other atoms can be chiral, but this is organic chemistry. Their only chirality is going to come from the carbons. Higher level courses will start teaching you how to identify chirality in other elements. And this is where you start seeing more rigid definitions, like it lacks an inversion center. Other questions? All right, you're welcome. All right, since I'm not really seeing other questions, we'll just cut this off about 10 minutes early. Again, if you have questions and you're not able to make a live stream, please feel free to email me. I have no problems answering your questions at the start. Again, I will try to be good about preferencing Orgo 1 versus Orgo 2. As always, make sure you're doing the discussion boards. The discussion boards do count towards your attendance in the course. So if you're not doing the discussion boards, you're kind of absent and you'll be dropped from the course. Also, keep working along on the homework. Homework's kind of posted in chronological order to kind of get you moving along and keeping you pace in the course. Discussion boards are also going to keep you on track in terms of the course. Again, with the lab this week, this is not a test. This is meant to help you understand the material. It's meant to kind of give you mandatory practice. When you come to the lab this week, you'll do the lab and you'll have until next week to submit your answers. Because of that, feel free to ask questions during the live streams or email me questions, or you can meet with me one-on-one if you really need to, and we'll go through how to answer those types of questions. It's important that you understand how to do the drawings, understand how to recognize chirality, because when we start stepping into the next material, which is characterization, this is where a lot of your ability to draw the structures and your ability to kind of intuit where hydrogens are, where carbons are, is really going to pay off. So I will see you all tomorrow from campus. Thanks for showing up.